Hey everyone, I'm Mokshada Gupta, and I'll be presenting on the interval scheduling problem. The solution to this problem runs in linear time, or it means that it has scope and complexity. Now, when I say intervals, I don't mean the ones from the movies. It in this context, an interval actually represents a period that is characterized by a discrete start and a discrete end time, and we can easily derive the duration of this period by just subtracting the finish time from the start time. Now, since I said that I'm not talking about the intervals from the movies, how does this problem apply to real life? Why should we care about interval scheduling? Well, imagine that you work at the registrar's office and you have all these people trying to book a classroom on a specific day for their events, and your objective is to make the bookings in a way that you are able to schedule as many people as possible without causing any overlap between their events. Over here, you can see that this is going to be a more difficult task than you would think because these three events they conflict. So you can only accommodate some of them, and then some of them would need to be accommodated to a different classroom. Now, to make this decision, the first thing that you would do is that you would start by arranging all these events in some way that you could, make sense of them. How would you do that? Like, would you start by sorting them out by the earliest finish times, by the earliest start times, by the shortest durations? But I'm going to spoil the answer for you and give you the algorithm. The algorithm that you would use is the interval scheduling algorithm, where we begin by sorting the input with the earliest finish times first. We initialize a empty set, which is going to be a returning set, and we start iterating over the our sorted input pool. Now, while this sorted pool is not empty, we will pick the event with the earliest finish time, and as I said, the sorting makes this easier. We will add this chosen event into our returning set, and we will remove all events that conflict with the one that we just chose from the list, and we will keep doing this until we have exhausted all the events that we could pick and choose from. And ultimately, if you follow this algorithm, the set that you build up is going to be your optimal solution. Now, as I was talking about sorting, I said that all these inputs must be sorted by earliest finish times. This is because our objective is to schedule as many events as possible. And you can see over here at each iteration, we don't really check what we did at previous iterations. We just kind of make localized decisions and hope that we end up at a global maximum. This is why we would characterize this algorithm as a greedy algorithm. And I said that the input must be sorted by non-decreasing finish times, so which means earliest finish times first. But what about the other rules that I mentioned? What about choosing events that start earlier or the ones that have shorter duration? Well, we have counter examples to prove that these two rules would not work. For example, for the first one, over here you can see if you were to pick the blue event, since this event starts really early, but it is of a really long duration, you would miss out on the green and the purple event. But you wouldn't really know not to pick this event because you're just going by like a one-dimensional rule. You don't really have a global view, and you would end up with a solution set of length 1 when you could have had a solution set of length 2. Now, same over here. If you were to pick a event with the shortest duration first, you would end up picking the green event over here, and you would miss out on the blue and the purple events, which are of longer durations. But since they kind of overlap with the shorter duration event, you wouldn't be able to see these, and you'd miss out on the optimal solution again. Now, I did say that this algorithm runs in O of n time, so let's ignore the sorting step for now and analyze the runtime of the actual algorithm. I have written it out over here in pseudocode form from the more logical algorithm that I presented before. We can see that the initializing it to the empty set and initializing a finish pointer is actually just taking an O1 amount of time, and just iterating over you see over here n events. This is going to take O of n amount of time, and returning an optimal solution that can be at most of length n is by value it was also only going to take O of n amount of time. Now, when I said linear runtime, I meant that it assumed that the input that was given into the algorithm is going to be explicitly sorted. If the input is actually not explicitly sorted, you would have to add a sorting step into the algorithm, which would sort it with earlier finish times first. And with that, the algorithm would become of n of log n time. This is because we know how to do algebra on runtimes, and we saw that this actually just takes O of n time, and we know that the runtime of the quickest sorting algorithm that we know takes n log n time. And since n of log n is obviously bigger, that term is going to dominate, and we can say that the entire, in that case, the entire algorithm will be of the order n log n. And I just plot these two functions on Desmos over here, and you can see how the plot of them, differs, and tau and the login factor adds up quite fast. Now, to revisit the example that I just gave, we can see over here that we are able to schedule through this algorithm 5 events. If you were to schedule, and if you were to schedule this event, you would have missed out on both of these, and you would have ended up with a solution set of length 4, which is like less than your current solution set of length 5, which means that the algorithm that I presented will lead you to an optimal solution. Thank you so much.